Okay, I think students are still coming, but if you have any question, let's take maybe 1 or 2 minutes before we begin. If you have any question, you can ask. Oh, one question I would like to ask you guys. So I know that a lot of students are having midterm exam and quite busy these days, right? So for the next written assignments, we are thinking to release either maybe mid this week or maybe next week, early next week. So I would like to get how is your workload right now in terms of course workload, right? So is midterm over for most courses, and when will it be over? Anyone can give me an idea? Because I don't want to release assignment when you are having other midterm stuff.
I can't speak for anything else, but the advanced algorithms midterm is on the 27th.
27th. Well, we cannot wait for that long. So
I didn't think so.
yeah. So yeah.
My midterm is also the same one, the advanced algorithm on 27th. So.
I see. Maybe we have to release before the midterm. Okay. So yeah. Thank you. Okay, let's begin. Yeah, so last time we talked about univariate data, right? So basically, if you remember, we talked about univariate functions, which means if you look at, you think about, let me see. Oh, just one moment. I think I'm in the wrong panel. Yeah, here. Okay. Somehow it didn't work so well. Just one moment. Okay, it finally works. So if you recall, let me open my pad. Okay. I think I should change the mode. Okay, this one works. Okay. So basically, univariate data means that we are doing something like y equal to fx. Okay. Well, we have a parameter theta, but this x is univariate. Okay, this x is univariate. Now we're considering multivariate data. Okay, because we are considering multivariate data, this x now becomes a vector. Okay, this x is a vector. Okay, so this will be a little bit more complicated in terms of the shape of the function. Okay, the form of the function, because now it has a multiple input, right? x1, x2, x3. This is also what you see in, for example, in scikit-learn. Okay, in scikit-learn you see something like a table, right, with many columns. Each column is also called an attribute or a feature or a variable. Okay, they are all the same. Okay, so for example, if you see a table, okay, you have features x1, x2, blah, 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 and you have data tuples, okay, data records. Okay, right. So each of these can be called an attribute, okay, in relational database. Right? For example, okay, we can also call it features. Usually in machine learning, we call them features. Okay, and if you think about from optimization point of view, you can also call each a variable, right? Because here this will be the feature value or variable value for this record. Okay, this will be the variable or feature value for x1 for this record. Okay, so this is the setting we're talking about. The reason we call it variables is because you think about functions, right? This is the input variables, right? And we have seen this before. So basically, we are assuming a table, something like this. So let me, I think now, let me try to use Zoom's functionality. That will make things a lot easier. Yeah. So you have n data items. Okay, so that's n. Okay, again, in machine learning, we will always use a parenthesis because otherwise you can interpret like a x to the power of n, right? Time x1 n times. Okay, and so this is n records. Okay, in the table, and we have d features. Okay, d features. So this is the first column. This is the second column, etc. Okay. Yeah. And so we have, let me see. So now that we have, let's say, let's say we have 2 points, for example. Okay, the first point is I think I still need to switch between writing and listening. Okay, so for example, if we have the first point x1, x2, x3. Okay, this is the 3 attribute table. Okay, the second, let's call it maybe y1, y2, y3. Okay, in the same 3-dimensional space. Okay, in general, we're considering d-dimensional space, right? So what will be the mean of these 2 points? What will be the middle point of these 2 points? Who can answer me? What will be the middle? Let me see. Why I cannot see my pen here? Oh, unfortunately, I think Zoom student work quite well. Let's still try to use the pen function. Okay, because sometimes the pen will be missing. I cannot locate it. So let's say we have x1, let's say the first point. Okay, maybe use this notation. x2, the first point, the first record. x3, the first record. Okay, and we also have another data item, the second row. Okay, oh, sorry. How can I erase it? Let's just call it 1. Okay, and this is the second row. Okay, x2, the second row, x3, the third column, but for the second. Okay, what will be the middle point then? Who can answer me? That's in 3-dimensional space. We have 2 points. Right? What's the middle point? What's the mean of them? Yeah, I think it's pretty clear, right? So it's x1 plus x2, x1, right? The first dimension, okay? Divided by 2, okay? Right. And this is the first dimension. Okay, the second dimension is this plus this divided by 2. Okay, over here. This plus this divided by 2 over here. Okay, so maybe it's not so clear. We can use another notation here. Right, so if you are more familiar with three-dimensional space using XYZ, then we can say something like this. Right? So if you have x1, y1, z1, okay? So this is first point. This is second point. x2, y2, z2, okay? And all the way you have 3-dimensional point. You have, for example, xn, okay? yn, okay? And zn, okay? And what will be the mean point of them? For example, what will be the first dimension? It will be n, then the x1 plus all the way plus xn, okay? Right, so this will be y and z, okay? So we are talking about this, right? So this is called the mean vector. Mean vector of these is this vector, okay? So this is basically what we are saying, that along each dimension, okay? Along each dimension, you take the mean, right? And then you listen here for d dimensions, okay? Then you get the mean vector. Right, so if you think from 3-dimensional space, it's much easier for you to understand. Okay, and there's another concept called covariance. Okay, covariance is a little bit different, right? So covariance is saying that, for example, if you remember what is variance, right? So variance, let me see, maybe there will be a variance concept. Okay, so here's a variance of a variable x I. Okay, but keep in mind that variance is just for one of the columns, right? So for the ith column, xi, the ith variable, we have this, okay? So for each occurrence of the attribute value, you minus the mean, which is the column, the ith column's the average value, okay? But this is how far each point is to the average, right? And then you will square them, okay? You square them, this is sum of square error in some way, right? So then you take the average, okay? So this becomes your on average each point, what's the bias square, okay? So this is the variance, okay? But this is only for the ith attribute with itself, right? So if you think about 2 different columns, okay? Let's say in the table you have the ith column, you have the jth column, okay? And then you want to see how these 2 variables, right, xi and xj, are correlated with each other. For example, yeah, I see my internet is unstable. Can you still hear me?
No, sir, you're breaking up. I can't hear you.
So where did I stop?
I think I understood until variance, and after that, it just started cutting out.
Oh, okay. So yeah. So let me reiterate what we.
Yeah, we couldn't hear the voice properly. Sorry.
Oh, okay. Let me redo this. Okay. So I hope the internet will be better. Okay. So for example, for the variance, I think everyone should know this is the case, right? But this is just for, let's say you have a table, right? You have a table. You have xi, xj. These two, the ice feature and the race feature, right? So they have different values, right? So they have some so-called correlation or covariance, okay? So which means if xi is big, y, whether it's also big, right? So if you think about a stock market, right? So whether, for example, Apple is selling good, whether the Facebook is also rising in price, right? So if Facebook is doing bad, whether Apple is doing bad, right? So if they're highly correlated, so this value will be big, okay? If they are totally independent, this will be 0, okay? If they are negatively correlated, let's say Apple is good, then, for example, the Facebook is bad, and they are negatively correlated, okay? So it will be a negative value. So how to define this, right? So by the way, here, this is the definition of variance. It will always be with itself. So it will not be negative, right? If you and yourself, you will always be in some way correlated, right? Larger than equal, okay? But now if you have two columns, the first column is the i's column, the second is j's column. So then you, instead of square itself, you have two terms, okay? Your I minus your mean and your j's value minus your mean, okay? And you take the expectation just like before. Okay, this is the expectation just saying, hey, each row is like this, right? I take the expectation of a sum of rows and divide by n. This is the expectation, okay? But of course, this is kind of square inside, right? So yeah, so this is what we have here for covariance, okay? Because now we have multiple tables, okay? Right, a table with multiple columns. So we do have the covariance concept.
So
right?
Professor, so covariance is only between two columns, or it can be between multiple columns?
Only between two columns, okay?
Thank you.
Just the I and the J, okay? Two columns. And these are actually hidden variables, but they are they present different values in different instances, okay? So this is quite a common, actually. There's another concept called correlation we will discuss shortly, okay? So these are actually quite often used. For example, for gene expression data, right? Whether two genes co-express. Let's say this is one gene that control one functionality of your body. The second gene also, like if you do different tests, they kind of activated, always activated or inhibited together, right? So then you go say they are highly correlated, you will add an edge between them. Okay, this kind of gene correlation can be used to find for particular disease activation, whether those genes can be targeted for some drug, etc. Okay, this is quite often they use. Okay, so and there's also other definition of correlation, right? So we are talking about maybe Psn correlation. There's also other kind of correlation. Okay. Yeah, before correlation is defined based on covariance, by the way. Okay, covariance. And the one thing that you need to pay attention is this. Okay. So we know immediately you should keep in mind this. Okay. So this variance can always be written as your variable square, take the expectation, minus your expectation of the variable squared. Okay, square we write out before e. Okay, for this kind. So this is another way to compute the covariance. They are equal. Okay, I hope you remember this in your, for example, probability theory course. Okay. But if you don't remember, we will derive it here, right? So you can see this is quite similar form, okay? Right, so it's just the I and the J, right? So the way to derive it is just think about this term. If we expand it, what will be the result, right? So the first term will be xi, xj, okay? And then we have xi times minus mu j, okay? So this is minus xi mu j, okay? And then we have this minus mu I and xj. So we will have minus mu I xj, okay? Okay, and finally have minus mu I times minus mu j, which is plus mu I mu j, okay? Right, so then you will take expectation, right? So you know linearity of expectation is equivalent to take expectation over each item, okay? Each item. and takes this expectation over this is itself, right? So, but let's look at a particular item here, okay? So this, because the handwriting is a little poor, it's not so convenient to write it. Let's take a look at it, exactly what it is. This is xi and the mu j, okay? And mu j, we know it's a constant, so we can move it out, okay? We can move it. So this is expecting xi. What is expecting xi? This is exactly mu I, okay? So this term is mu I mu j, right? So this is like a minus mu I mu j. This thing is the same. This mu I can be taken out, expecting mu j, which is again expecting j again. So this is the minus mu I mu j, minus mu I mu j, and plus 1 mu I mu j. That's minus 2 plus 1 is minus 1. So that's what we have. Okay. And usually we assume this correlation is not exactly 0 for all the features. Okay. Because if that is the case, then they become naive Bayes, right? You don't need a material analysis. Okay, everything is independent. Okay, so that's a simple case. We will see that in later analysis. And another important thing to keep in mind is that when even though we have D columns, okay, in Polish theory we use variance, right? Variance is quadratic, right? Which means we actually really consider just 2 columns, okay? Also, the more complicated correlation between multiple columns are actually captured by the every pairwise the correlation, okay? And then we can capture the more complicated correlation, okay? So, and each one actually we are measuring how they are linearly related. Why it's linear related? Because this is a linear function, right? This is a linear function. How far away you are from the mean for attribute I and also attribute J for the same row in your table, okay? For each row we are talking about. You have this, right? So when you look at enough rows, then you know how they are correlated, okay? Any questions? Because the row is taking expectation divided by n, okay? Yeah, if not, we will move on, right? So another concept is covariance matrix, right? So why we are talking about it, right? So because you think about it now, right? So previously we have this, okay? We have sigma ij, which is the covariance of i's column, j's column, right? This is they are equal. Okay, they are equal. You can see this times this and this. If you swap them, it's the same. Okay, and if you look at the variance of a particular, let's say the i's column, right? It's really something like this. Okay, the reason is very simple, right? If you put I and I replace j, you get exactly this, right? Square. Okay, you get this, right? So this is just a simplified notation of sigma I, right? Now we have I, which can be one of the D columns, okay? And J can also be one of the D columns, right? So we basically get a matrix, right? D by D matrix, okay? So basically we have something like this. Let me call all the.
I have one question, Doctor.
Okay.
Yeah.
Yeah.
This covariance only use the linear model only?
Yes, this is a definition. Okay, so you can model nonlinear function. Okay, but you will.
The linear function. Okay.
Yeah, you can model nonlinear function. Covariance, for example, the Gaussian distribution using covariance matrix. We'll see later. Okay, but those basic modules are defined using linear relationships. It's okay.
Okay.
Yeah.
Thank you.
Okay.
Hey, the sigma 2(1) versus sigma 1(2), does that end up being a different value?
No, they're the same.
Value?
Yeah, so they are the same. You think about sorry. You think about sigma ji is just swapping these two, right?
Okay, I see.
Yeah, so it's swappable. Okay. Yeah, so it's a symmetric matrix, which means along the diagonal, these two are the same. These two are the same. Okay, I hope you can see it, right? And why we can represent it like this? This is very important, by the way, because when you code in MATLAB or you code in NumPy, okay, so often you will. So basically, you need to know that your each row item, right, minus the mean vector, okay, so which is this one, okay, and if you get this, and you take the, you take the transpose, okay, and then this actually gives a matrix, okay, and then if you have let's say n data items, you just sum this matrix, n matrix together and divide by n, okay. So basically, what I'm talking about this, okay. So firstly, you need to understand. Let me try to call the pen. Okay. If you don't understand, I will go through it, so don't worry. Okay. So this thing is a D by D matrix. We'll see why. Okay. This is D by D. Right. So we'll see why this is D by D. Okay. And now this is just for one, because before your expectation, we are just talking about one row, right? If you have n rows, okay? Basically, for each row, you will generate a matrix d by d, okay? Plus another d by d, okay? Let's say you have n rows, okay? Divided by n. This is your sample covariance matrix, right? Any questions? Okay, if not, let's think about what is this? Why is this thing will be equal to this thing, okay? And the reason is very simple. If you treat this as a random variable, then it becomes a vector. Okay, this is a vector, this is a d-dimensional vector, right? So this minus is also a vector. You think about it. What's the column vector times a row vector? What's this? We have gone through this before. What is this?
Becomes a single value.
No, it's an auto product. Value in the product. Okay, d by d matrix. Yeah. Okay, so again, so if you don't know this, let's just think about x times x transpose. Okay, we talked about it, right? X is a column vector, which is x1, x2, blah, 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 xd. Okay, transpose is x1, xd. Okay, so this will give you a d by d matrix. Okay, so this is because this is d by 1, this is 1 by d, right? D by 1 and 1 by d gives you d by d. Okay, so the first row times the first column gives you x1 squared. Okay, the first row times the second column, which is x2, gives you x1, x2. Okay, and the first row times this column gives you x1, x2. Okay, and in the future, you need to know something like this, right? So this thing is in the product. This is actually this thing is actually the L2 norm, okay, of your vector. So, but this thing is, if it transposes on the other side, right? So this is the out product. Okay, it's a matrix, right? And actually, this does not have to be itself, right? The second x can be y, okay? And in our case, we are talking about itself, right? So let's say the last one should be the dth row times the dth column. It's kind of very similar to this shape, right? So there's only one step away, okay? So because here we are talking about, if you think about this minus mu, right? So if you look at this term, okay? This term is basically, we are saying this should be x1 minus mu1, okay? Times x2 minus mu2, okay? Something like this, right? This one, this is the first, no, this is the first row, second column, okay? So this is I is the first column, the first variable. J is the second variable, x1, x2, okay? Now, you see, what is the expectation of a matrix, right? So, this is the matrix, okay? We just see this in matrix. Expectation of a matrix is just takes the expectation over each element in the matrix, okay? Each element. Now, what will be expecting this? This exactly sigma I want to, okay? So let's go back. Okay, this is exactly sigma I want to. Right? So I hope you can see this. And why expectation of a matrix is just an element-wise expectation, right? It's a generalization of the vector, right? So if you look at the vector, right? So this is really, go to high-dimensional space. Instead of getting intuition in the high-dimensional space, you get intuition from low-dimensional space. Okay, this is x1, this is x1, xd, right? So this mean vector expectation is taken to each vector. Okay. I hope this will give you some feeling, and when you see enough of those analysis, you will be able to read those more complicated mathematical papers on machine learning. Okay, it's just stay with me and see more of this derivation. Okay, and we talked about covariance is not actually often used, right? So, for example, if you have the first variable is age, the second is salary, for example. Usually they are more positively correlated, right? So as you become senior, you probably get higher pay for them, right? So for these two attributes, xi and xj, right? Age and the salary for them, right? So if you think about the salary, the number is going to be maybe at least 1,000, right? So it's very big, okay? And if you look at age, at most 100, for example, right? So for a typical person, okay, it's not on the same scale, okay? So this scale, we want to cancel out the effect, right? So that's why we are doing something like here. We'll normalize out their scales, okay? Right, so this sigma ij is basically what we just computed here, but we want to normalize the magnitude of each attribute, right? So this is age, which you divide by kind of like 100, okay, standard deviation of that, maybe 50 or something, okay? And we also want to normalize by the second attribute, okay? So this gives us a concept called correlation, right? The next thing about correlation, which we will often wrote as rho ij, or you say CORR instead of COV. COV is covariance. Okay, CORR is correlation. If you see just one R, COR, it also always means correlation. Okay, most of the time. And so the correlation has a nice feature that because it's normalized, right? It's always between -1 to +1, right? So if your two attributes are totally irrelevant, right? So for example, for the first row, for this person, the age is high, but the salary is low. For the next person, the age is high, the salary is also high, right? So there's not really a relationship between them, right? In that case, your correlation will be close to 0, okay? If, for example, your age is high and your salary is also high, right? So they are correlated, and the more correlated is the more closer to 1, okay? If on the other hand, if your age, as you get older, you get lower and lower pay, right? So then your salary and your age is negative, okay? So negatively correlated. They are still correlated, okay? Only 0 means they are not correlated. It's okay? So this concept is called a Psn Correlation Coefficient, okay? So this actually still cares about the absolute value, right? So if you look at our definition here, these things are actually still absolute value, right? So however you are from the mu, okay? Sometimes if you have two variables, right? So let me give you an example. Just let me call out the pen again. So let's say one variable as, it's not linearly related, right? So one variable increases linearly, another maybe exponentially. Right? So as this variable increases a little bit, this variable increases a lot, right? So they're still correlated, okay? But this will not be captured well using a linear relationship, right? So because here we talk about covariance correlation or linear, okay? So instead of using Pearson correlation, okay, we have another correlation called Specimens Correlation. Okay, so let me get something here. So this is actually not relevant to us right now, maybe more related to some basic knowledge, but I think it's good to show you guys. Okay, so let me try to move things there. So so this actually, you can see the name, it's a rank order, okay? So what did this mean? I think we should know. So this means that if your correlation is not something linear, it's like a very non-linear, right? So, but you can see that it's still linearly correlated. This is still correlated, positive correlate, right? As x increases, y is also increasing, right? So maybe a bad option is to use your rank, okay? So you sort the value along x1 and also x2, just using their rank. So the largest value becomes 1, the second largest becomes 2, etc. For the second attribute also this. And then you compute the correlation between their ranks. Okay, so this is where we are. Why cannot zoom in? Yeah, here. Okay, so these are the ranks. Okay, after we get the ranks, we compute this. Right. So this will cancel out the nonlinearity here. Okay, if you have that the variables are not linearly correlated, you can use Specimens correlation. Okay, but here we will not touch that. Okay, throughout this course, we just look at this Pearson correlation. Okay, so another important thing to pay attention is that correlation is a loose restriction than dependence, right? So if you say x1 and x2 are independent, they are totally independent, okay? So you can factorize them out in probability, right? But correlation doesn't have that guarantee. It's just saying that linear relationships are independent. Okay, so this is just saying that they are linearly not related. Okay, it doesn't mean that in high order they are not related. They can be still related, right? If it's independent in any order, they are independent. Okay, so here's example. Here is example showing this, so that you can pay a little bit more attention to correlation is zero doesn't mean that they are independent. Okay, so here you consider this distribution, right? So if we write it's a PDF, it's something like this. Okay, it's a uniform distribution. This U means uniform distribution from -1 to +1. Okay, uniform is their PDF, so density is the same, right? So what will be the height? Who can tell me what will be the height here?
Should be 1/2.
Yeah, 1/2. 1/2. Okay, because 2 times 1/2. So the height is 1/2. So with the 2 is 1. Right? We know that the area of the probability is sum to 1. Okay, so this is 1. Okay, now let's think about this variable. Okay, so the expectation is what? The expectation is 0. Okay, now let's think about another variable. Let's say maybe in your table, the first is age. Right? You can create another attribute called age square. Right? So that's a y. Okay, then we can show that they are actually their correlation or covariance are actually 0, but you cannot say they are independent, right? So this obviously depends on this. Okay, let's see why. Right. So firstly, let's think about expectation of y. Okay, y is x squared. Right? So if we take integral from this range to this range, the density is 1/2. Okay, the density is 1/2. The value here is x squared. Right? So this, okay, from -1 to +1. Okay, so what will be the result? Okay, so this will be equal to -1 to +1, 1/6, right? Dx cubed. If you cannot see it quickly, just think about what is d cubed. Okay, d cubed is 3d d squared, right? So, and now if you think about it, right? So now because you don't have 3 times, right? So if you just have sorry. So how to say this? This is actually x squared. Yes, 3 times dx squared. So let me see. Yeah, 3 times d cubic. Okay, so equal to sorry. The d cubic is 3 dx 3 minus 1. Okay, it's 3 dx squared. Okay, let's do this, right? So actually we should have some notation error. Okay, so let's ignore this. Okay, a long time didn't do the integral. Okay, we should just say something like this. Okay, so we are still taking derivative x. Okay, we are taking derivative x. It's just that it's x. How to say this? X squared dx is equal to 1/3 dx cubed. Okay, right. So because if you take the
It's x cube over 3 dx, right?
What?
It should be x cube over 6 dx. X cube over 6 dx.
Yeah, you don't have this 2. This is 1/3, right? So because take a derivative, x3 take derivative x is 3x squared. Okay. Right. Is okay? Yeah. So here let's clarify. Okay. So if you have x cubic, okay, you take a derivative to x, it's equal to 3 times x squared. Okay. So in this case, basically if you write in this d kind of form, right? So it basically says that x cubic d is equal to 3x squared dx. Okay, because it's dx means take a derivative x. Okay, and now this is x squared dx. Okay, And now if you write it dx cubic, you actually own a factor of 3, so it's 1 by 3. Okay, and another half 2, so this is 1 by 6. It's okay? Yeah, that's clear. Okay, so now that we have this, basically we are here. Okay. We are saying that we are having -1 to 1 and 1 by 6, right? So dx cubic, right? And you can pay attention, okay? X cubic is something, so if you take integral, this thing goes on, right? So, and this is really saying that it's 1 by 6. And, if you go from negative to 1 and take the integral, it's really something like a x cubic, right? So using 1 cubic minus 1 cubic. Okay? Right. So this will give you 1 by 6 over 2, which is 1 by 6. Right. So put simply, the expectation of y is going to be something positive, right? 1 by 3. It's not difficult to understand, right? So, if your original range is between 0 and 1, then this will square is still 0. All these will give more than 0, right? So if you think about the expectation of this, it will be something positive, which is 1 by 3. Okay? And then lastly, let's look at the EXY. Okay, why we are computing this? Firstly, okay, so the reason we are computing this is we want to use the correlation formula here. Okay. I hope you understand why we are talking about this. Okay, so because let me see. Because this, okay, because this, right? So this one is basically this one, okay. And it's not difficult to see if you have expectation of x times y is x squared, right? So this is x cubic. Expectation of x and expectation of cubic are always 0. The reason is very simple, okay? Because it's symmetric, okay? If you're x, then -1, 1, it's symmetric, right? So, and it's uniform distribution, then this thing cancels with this thing, this thing cancels with this thing, this thing cancels with this thing, okay? Finally, if you integral them and take sum, it's 0, okay? And the cubic is similar, right? So although it will be like this will be 1, will be very 1, right? If you have 0.1 here, it will be 0.001, right? Much smaller. Okay, its shape will be something like this. But again, these two are symmetric. So this cancels with this cancels with this. Okay, so it's still 0 because it's symmetric along the y-axis, right? So this side.
That's a square function, isn't it? That's not a cubic function.
Oh yeah. So sorry, I'm talking about. Let me see. I mean, the x value is actually goes down, but the magnitude is. Let me see. No, so this is not square function, okay? Let me see. Keep in mind, we are talking about x is this axis, okay? This is 0, okay? This is more than 0. This is negative, okay? This is negative, right? Well, here, this y-axis is the probability, right? But the probability will never go negative. You can ignore this, right? So that's why we have this. Okay? If you have cubic, 1 cubic is still 1, okay? If you have 0.1, cubic will be 0.001, okay? So that's still small, okay? But they are symmetric, okay? Negative will be negative, right? So these two cancels if you time their probability, right? Density, which is the same also, because these probability are symmetric. This height and this height is the same, okay? So put simply, in your calculus class, there must be a theorem saying that if you're, maybe not just calculus, maybe also the probability theory, if it's a symmetric along y-axis, right? So the expectation will be 0, okay? Because left side cancels with right side, right? Because this is negative value, this is positive value. These values times their probability height is the same, okay? So they cancel. Any questions? All right, so if you have no questions, let's pull this value here and pull this 0 here. I understand this is not 0, but it doesn't matter. We times 0, this term is 0. Okay, this is already 0. So the correlation is what? Is 0, right? But obviously they are not uncorrelated, independent, right? Y is dependent on x. Actually, it's exactly x squared. Okay, so that proves that correlation is 0 in this example doesn't mean that no, doesn't mean they are independent, right? Any questions? Okay, then let's continue. So previously we are talking about variables. When we talk about variables, right? So we are really assuming that only d-dimensional variables. There are d variables, x1 to x2, right? But in real data, we have samples along with t, right? So previously we are talking about the table has, right? So the first attribute, the second attribute, okay? And each is a random variable that can take those column values, right? Now we can put in those actual values we observe, right? So this will give us the let me see, the sample mean, okay? Sample mean, right? So actually still take expectation, right? So like but now expectation is really sum them up and divide by n, okay? And we also have the sample covariance matrix, right? So as I said, you have n such matrix, right? This is the auto product. It will give you a matrix, okay? You have n such matrix summed together and divide by n, right? So this is your sample covariance matrix. This is how you compute the sample mean and the sample covariance matrix when you see the table like before, okay? N rows and d columns. And in particular, this covariance value between the I and the j's variable or features, right? If they are the same, you can write it as SI squared. Okay, this is sample variance. Okay. And there's also correlation, right? If you have sample variance and you divide by a sample covariance divided by each sample variance of the columns, right? You get the sample correlation matrix. Okay, this is not commonly used because for both sample mean and sample covariance matrix, you can get the unbiased estimator, but correlation, there's no unbiased estimator. Okay, so this is deeper in mathematics. We will not go through it, but keep that in mind. Okay, usually in this lecture, we will stop right here, sample covariance. Okay, any questions? If not, let's continue. Right. So what to do if your value, right, certain values in the table are missing? Right? So this is quite common. Okay. For example, if you think about here, right? So you maybe some value, let's say if it's a medical record, right? So but you didn't measure blood pressure in one exam, right? So then this will be a question mark. I don't know what the value is. Okay, and then you know, there could be multiple missing values here. Okay, so how do we handle this? So one way is to discard the whole row, the whole instance, if the sample, you know, we miss a value in this row. Okay, for example, if we have a medical record, but this value is not measured. Okay, this guy, this value measured. We just if we see for this row all values there, we take it. Okay, this will be deleted. Okay. But unfortunately, if in your medical record, maybe each time you just do a few exams, right? So you don't do all the exams, right? So most of them will be eliminated. Then that's not good, right? So this is not desirable. Okay, I think I can directly jump here. Okay, so this is not a good idea if the sample is small, right? So in that case, we need to do some so-called imputation, right? It's that data cleaning, right? So filling the missing values, okay? But they're missing, right? You cannot just say, hey, this guy's, you know, this guy's blood pressure is that value, right? So you need to at least get some educated guess, right? So some reasonable guess, right? So for example, if you say this guy height is missing, I say this guy is 100 meters, right? So this is not gonna work, right? So there are several ways. Okay, the first way is the best guess is mean. Okay, so the mean value. Okay, right? So average value of the current pool that has a value. Okay, another concept is mode. They are kind of similar, right? So here, let's look at it. What they mean. Okay, let me see. So let's consider the second attribute. Okay, it's the second feature. Let's say if this guy's value is missing. Okay, but all the other values are here. Right. So what we will do is we take the average of the other values, like the height, and then just to say the average height is your value. Okay, it's not gonna be correct, but it will fill the value. Then your machine learning model can run, right? Because machine learning model some of the machine learning model cannot take missing values. Right? Decision tree maybe, but a lot of models, you have to have some value, right? So that this value will not be too far away, okay? So this is a mean. What is mode, by the way? Let's use this column as an example, okay? The mode is actually the most frequent values there, right? So for example, if you have discrete values like 1, 1, 1, 2, 2, 3, 3, right? So mean will be what? Mean will be something around 2, right? So, but mode is 1 because you have 3 ones. The other is not majority, not the most frequent, okay? So the mode will be 1 in this case, while the mean value will be somewhere in the middle, definitely larger, okay? And yeah, maybe we can expand a little bit of this. Let me see. How come? I think we should have a browser there. Just let me do this again. Yeah, we will leave a browser here so that we can. Okay, so let's take a look at how in machine learning we will usually do this. Okay, so usually we have the pandas. Okay, and I think actually pandas will read the table and then you will fit the values. Okay, pandas. I think a fill in a function. Okay, in Python. Right. Whoa, what's happening here? Okay, so this is how you say here for which column we want to fill which values, right? So some of those question marks you can call them holes, right? You can fill 0, and there are different ways of fill. Okay, so like a backfill, pad, etc. So if you want, you can do some study, but there's like a mean, I think. I think we need to find the API. Is this it? Anyway, the fill NA is to clean some column values. Okay, let me. I hope I can find the proper API. Maybe that's it. Okay, so let's take it. Maybe we have to look at here. So yeah, I cannot find it right now, but actually, let's Google this. Python fill column with, let's say, mean with mode. Let's see how people say. Yeah, here's the example. Okay, so after you read the data column, okay, this is a column name. And then you can fill NA, and then you can fill like the most frequent content. You give it the content. Okay, so this is the mode, and probably okay. Let's say the mean. Okay, with average is a column. Okay, so here here is the example. Let me see. So by the way, when pandas read the CSV file, if your zero's value is actually not there, right? It's a empty value. It will think about it's a not a number, right? So then it will fill it. Oh, actually, this function takes a value, right? So you have to call it. I wanted the mean of this value, right? So if it's a data frame, then the mean of all the 3 columns, right? It's actually in our slide. It's this one, okay? It's a mu. Right? For every column we get, okay? And then we fill NA with mean, which means if you go back to here, so for the first column, you already have the mu1, right? So for every question mark, or we say and not a number, you fill with that value. Okay, for the second column, you use the mean of the second column. Okay, so there's some way to do this. But what I want to say is that you will typically use pandas to do cleaning, and then throw the model to scikit-learn. Scikit-learn's model usually cannot take missing values, right? So this is, yeah, this is what I want to say. And the fill NA is a function, okay? And this is the mean interpretation. you can also use mode. Mode is most frequent value. Okay, so, and the second is imputation by regression, right? This is pretty easy to understand, right? So you can, because, you know, if you come back to this here, this slide, you know, you observe for some of the data, you observe all their values, right? Then you can train a regression model treating a particular, let's say x2 as y, right? And once you have the regression model for those missing values, you can use the other attribute to throw them to the regressor and estimate this y value and fill it here. Okay, so this is another way to do that. And the last method is matrix factorization. Okay, so what is matrix factorization? Right. So maybe we can spend some time discussing what is it, so that you can. Actually, we will not cover that otherwise. Only in this place, maybe we will cover. Okay, I hope I closed the browser again. So sorry. Yeah. So let's look at matrix factorization. Okay. I hope they have something there. Okay. So here is let me see. There should be some. Wikipedia is not so user friendly here. Okay, so let's see a example here. Okay. So here what is what we want to do. Okay. It's a triangle. I think we do have the. What is this? Maybe this one is okay. Yeah. So here's the example. Okay. So let's say you have the ratings a person to each movie, right? So then you will get a matrix, something like this. Okay. So each row is a person, each column is a movie, right? So, but this matrix can be huge, right? You may have lots and lots of person, right? Maybe 1 million users, right? Movie, maybe 10,000 movies. Okay. So you need a lot of things to save them. And in meanwhile, maybe, for example, here, you know, for this guy, okay, this person, he only watched these 3 movies. He doesn't watch this movie and this movie, right? Because they are potentially 10,000 movies, right? So he cannot watch all of them, okay? So this is actually a data with a lot of question marks, okay? These are question marks, right? Your readings are really small, right? 3 star, 4 star, right? So some ratings, okay? So for this kind of data, we can call this as matrix A, okay? I think I need to use a pen. Just we call this matrix A, and we want to factorize it into 2 matrices. Let's say H times W, okay, or W times H. Okay, W times H, matrix multiplication. Okay, so what does this mean? So A, you think about A. Okay, so A is maybe n times n, which is very large values, right? So we can factorize into 2 matrices. The first matrix is n by k, okay? The second matrix is k by n, right? The result is still gonna be a matrix that is n by n, right? But you can use a much smaller dimension, right? If in the extreme case, the value k is 1, then this becomes an n-dimensional column vector. This becomes n-dimensional row vector, right? It's just the n values plus n values, right? Instead of n times n values, right? But you can increase k a little bit, right? Say so. So this is still, I think it should be HW, okay? Because H is height, right? Tall matrix, okay? This is n rows and k columns, okay? And this will be a fat matrix, okay? This is k columns and n rows, right? So this allows you to factorize, right? So, and after recursion, okay, after times back, you hope the values here to be relatively close to these values that you rate, okay? But because of your factorization, right, you after recursion, these cells will also have values, right? Then you use these values as a, you know, as the values there, okay? As the true values here, right? As the cleaned value, or even though they are missing, right? So this is actually used by recommendation. Let's say you want to say, hey, for this guy, whether he likes this movie or not, right? After factorization and time back, you see, oh, this is the high value. I should recommend this movie to this guy, this first guy, okay? So this is called matrix factorization. And the key idea is instead of making such a big matrix, we just have a few columns, okay? So this is called the how to say this? The rank of this matrix. You make this matrix a lower rank, okay? K, the rank is K, right? Because you can use K columns times K rows to get the matrix, right? So this is like a extreme case of inner product, right? Inner product is one row times one column gives you a matrix, right? Now you say, hey, it's not just a one dimensional. The data, the movie and the user actually is inherent by 4 factors, okay? And so you have more factors like this. These 4 are like the user dimension. This can be the movie dimension for them, right? So this is the idea, right? So again, so this is called the low rank approximation because this may be the rank could be n or could be n, okay? So here you lower the rank to k, right? So a way to do that is actually to do this is let me see. I think I should clear this, okay? So let me see. Let's hope that this guy has a thing here, okay? So what we will do is this, right? So you think about extreme case of out product, just one row, one column, right? So after time back, we want the error element to be relatively closer to y, right? For the linear norm, basically error element, the difference, square. This is for linear norm, okay? So this is how we time back the original x from this, right? So in general, we will have more than just a rank 1, okay? We'll have A will be k columns in one column, B will be k rows, okay? And then we have a rank k matrix and we want to factorize them and find this A and B. And if we time back, they are rather closer to A, right? We want to minimize this. This goes back to a optimization problem, right? So after timing back, it's rather close, okay? This 4.8, right? This is 1, this is 1.34, right? It's still rather close, okay? So I think this is a good example, okay? So the important thing about, yeah, this is the example of missing value, okay? And the important thing about, this is like movie rating example, okay? An important thing about why we need a multivariate calculus is this, right? So matrix. So this problem, this kind of Frobenius norm is very popularly used for this kind of optimization problem, because if you look at, you know, when we need to do derivative gradient descent, right? So then if you look at a norm, vector norm, matrix norm, okay, this is matrix norm. Frobenius norm can be represented as a trace of the matrices, okay? And the important thing of doing the trace, okay, doing the trace is that then you have another table, right? So you have then determined derivative trace, right? Then you can see whether you need this formula or that formula. And then you can use a matrix cookbook. Even though you're not so good at mathematics, you can continue and finally get the derivative in the high dimensional, even matrix dimensional space, okay? So this is the idea. Yeah, let's continue. So this is basically say we use a low rank, right? K dimensional. Assume there are K factors, not 1 million factors or 10,000 factors, right? So then we will be able to recover those question marks, okay? Any questions? If not, let's continue, okay? And yeah, as we said, this is the multivariate data, right? So the Gaussian distribution will be more complicated, right? Previously, we just have X1. Now we have X1, X2, X3, X4, okay? In this course, we will visualize things only in 2-dimensional space, right? So because, you know, you need a, you know, human can at most see 3-dimensional space, okay? And this dimension is for probability, P, okay? And so all you have is 2-dimensional for the 2 attributes, okay? So the Gaussian in 1-dimensional is something like this, right? 2-dimensional is something like this, okay? You see here, right? So like in one-dimensional space, right? So in one-dimensional space, there's a sigma here, right? So sigma is standard deviation. Here we have what? We have the covariance matrix, right? Now we have more than one dimension, right? So we have a covariance matrix, okay? And the absolute value of a matrix, there's no absolute value. This is a determinant, okay? The determinant, right? So I hope you know what is determinant, right? So if you don't know, usually we will do something like this, right? So if you have a matrix A, B, C, D, okay? If you compute the determinant of it, okay? It will be equal to what? Who can tell me? It's AD minus BC, right? Okay, so you use this minus. And I think in linear algebra, probably compute the determinant of 3 dimension, 3 by 3 matrix, right? But more than that, just leave computer to do that, okay? And this thing is, there are 2 features, keep in mind. The first is square, right? So it's because it's D by D dimension, okay? The second is symmetric, okay? Symmetric, right? So because it's covariance matrix, Ij and Ji, you know, it's the same covariance, okay? Right, so this is covariance, this is the matrix, but after taking determinant, it becomes a value, right? This is like absolute value in one dimension, okay? And then once it becomes a value, it's more like your standard deviation, right? So, but this is a squared, okay? So you need to take a square root, right? And again, previously, if you remember, we have square root 2 pi. Now we have d dimension, right? So we have this d times this, okay? And now let's look at exponential, right? So on the exponential side, previously what we have is this, right? So we have 1 by 2 sigma square x minus mu, okay? Square, something like this, right? On the exponential, right? So now it's something similar, right? So keep in mind, this is what? This is a quadratic form in scalar space, right? So this is quadratic form in more than scalar shape, right? It's a high dimensional scale, quadratic form, okay? As we said, 1 row times a square times a column is 1 by 2, which is this one, okay? And you know, this one negative 1 by 2 is this negative 1 by 2, okay? The only difference is that now the variance is replaced by kind of covariance matrix, but it's at the bottom, right? So in scalar case, at the bottom means in the high dimensional case, it's the inverse of the matrix, okay? Inverse of the matrix. Inverse means if you times this negative, it's equal to what? Equal to identity matrix, right? So if you look at the special case of one-dimensional case, times is equal to 1, okay? This thing is also equal to 1, right? So of course here we have the square. I'm just illustrating the concept, okay? So this is how you, actually this is the one-dimensional case is a special case of this multivariate. Okay, so we have first seen a simple case, and then we generalize to this distribution. Again, don't ask me why this is, right? So it's a probability stuff, right? So you ask Gaussian, okay? Or ask your calculator, I mean, probability theory instructor, okay? So just let's take it for granted, and let's move on and look at some stuff here. Let me see the time. Okay, I think maybe we can, let me see. Okay, let's take a 10-minute break. Okay, let's come back in 16:15, and then we continue. Today, I think we need to move a little bit faster so that we can finish this slide, right? So, okay, if you have any question, you can ask me now. Otherwise, yeah, I will see you 10 minutes later. Thank you. Oh yeah, taking this time, I get some feedback from you guys. So can you guys follow? Because it's a little bit mathematical right now, right? So we probably will not go beyond this. Okay, so this is the most mathematical lecture in the whole course. Okay, and unless you really want to dive deep into like optimization and machine learning theory kind of stuff. Okay, so so there are different levels of machine learning users, right? So firstly, the first level is scikit-learn users. Okay, you are familiar with the models and the hyperparameters, and then you know some tricks like how to load pandas, clean the data, and then you will be able to use it, right? So and how to tune the parameters, like grid CV. Okay, and this is a shallow model, right? Deep learning, you need to know scikit-learn. No, you need to know the TensorFlow, Keras, or PyTorch. Okay, PyTorch is easier to use, TensorFlow is faster. Okay, and then these libraries are way more difficult than this, way more functions. Okay, and you need to have the clear concept of those things. Okay, and then you can write deep learning models, right? So publishing papers, etc. Okay, so this will, the library itself will require maybe 1 year to get familiarized. Okay, and on the theory level, okay, so these are the application level, right? So on the theory level, let me see. Yeah. On the theory level, you need to know these optimizations, right? So nice thing about TensorFlow, PyTorch is that they hide those theories, right? If you know a function like cross entropy or some convolution, they actually takes a gradient for you. You don't take gradient yourself, right? So they actually did that for you, and then using Psn rule to hide those details. But here we will give you some practice of these things because we are teaching the fundamentals, right? But a lot of times, if you want to design new modules like matrix factorization, those kind of things, right? So some of them may not be in TensorFlow, PyTorch, right? You need to write your own modules, right? So this will be a lot more difficult, right? So write a new layers in TensorFlow. There are different ways. One is using existing layers. Then that's easy job, right? So it's a combination of existing layers. Each can use chain rule to back propagate. That's good. Okay. Another possibility is totally this operation new. Then you need to kind of open up like their primitive layers, right? You define the backpropagation gradient operation. Then you need something here to help you, okay? And another thing is that you totally work on the mathematics side. Okay, it's not the theory yet. There's a learning theory that is totally theory. Okay, there's a conference called NIPS for that. Okay, more machine learning. There's a conference called ICML. Okay, International Conference on Machine Learning. Okay, and then the application side you have like a CVPR for computer vision, right? So video, images. You have ACL, natural languages. Okay, so application side. Okay, robotics. There's another direction, right? Reinforced learning, those kind of. Okay, and so in more general AI, you have like a triple AI, Agile Kai, those kind of conferences for research. Okay, and for projects, if you don't need novelty, then these libraries is what you need to know most. Okay, so in machine learning, we will teach scikit-learn. Hopefully, in deep learning, you will self-study a little bit of this, or hopefully, when you take the course next semester, for example, you will pay more attention to these libraries used. Okay, get familiar with what library, not just a theory. Okay. Yeah, so that's just to motivate a little bit why we are teaching this. Okay. Yeah, if you have any questions or you cannot follow somewhere, we can go back and just let me know. Okay, we can review. And we will take attendance maybe while in the second half of the course. Okay. And if you are doing machine learning research, here are the order. Okay, so Agile Kai, let me try to use. These are not specific machine learning conferences. These are the general AI conferences, right? So machine learning is a subset of it, okay? So these conferences are inflated significantly. So AGI is significantly inflated. It's like you get an AGI paper, you got 10 AGI paper maybe equal to 1 NIPS, okay? These days, unfortunately. And the review quality is going low, but they are still first tier, almost first tier, maybe 1.5 tier, okay? And if you look at, this is AI general area. If you look at, for example, so if you want to follow latest research, right? So if you look at a more machine learning specific area, okay? So there are 2 conferences. One is called ICML. These are more on models, especially like graphic models and more some deep learning models, okay? And there's a NIPS conference. So the name is a little bit not so elegant. So they now rename it to new, probably this name, I don't remember. It's NIRPS, okay? So something related to neuro, okay? So NIRPS is quite mathematical, okay? It's pure mathematical, 10 appendix of mathematical derivation, okay? Unless you really like strong in math, you need to look at it. Okay, here the math we teach is like elementary school level. Okay, this is more like a maybe college level. If we think about people are working with college level mathematics, right? We are elementary school mathematics. Okay, these are must-know mathematics that we are teaching. If you want to be more than superficial secular, you lose. Okay, and so in the domain, there's also some conferences. Okay, like in computer vision, right, which is quite hot these days, self-driving cars, etc. Right, so there are 3 conferences ordered in this way. Okay, if you are looking at papers, you can go to this CVPR, okay, ICCV, ECCV. Okay, and for natural language processing, there are 2 conferences called ACL and EMNLP. Okay, so these are more application folks. And previously, there are traditional feature engineering, right? So now it's all flooded by deep learning. So this is also inflated significantly. Okay. Yeah. So the highest standard is ICML and NIPS, and then maybe here, and finally it's here. Okay. If you look for papers, it's like this order. But application-wise, maybe this is more important because it's a little bit more massive side. Okay. And if you got these paper rejected from here, they will accept your papers. So some of them, right? They ask for appending the reject papers in these conferences. Okay. Yeah, in case you are doing AI research. Okay, so I think the time is almost there. Let's continue. Right, so yeah, let's take a look. So this is actually the high-dimensional Gaussian distribution. And this is a multivariate generalization of univariate normal distribution. Okay, normal is a Gaussian distribution. It's the same. Okay, we are talking about normal or Gaussian distribution, right? It's a generalized of our previous univariate. We talked about Y. Okay, and there are so if you represent it, you will represent using the normal distribution mu and sigma. Mu is d by 1, the mean vector, right? And the sigma is what? The sigma is the covariance matrix with d by d, right? So now you can see that in high-dimensional space, the Gaussian distribution itself has d plus d by d parameters you need to train. Okay, it's not just like before, only 2 parameters in the scalar case, right? Because in the scalar case, this is 1, d is 1, right? So it's 1 plus 1. Okay, and yeah, so this is the probability density function. We just explained why. Okay, and like before, we will take a log likelihood, right? So this is just a one particular item. Okay, so what I mean is, let me see. So this is let me see, log likelihood. So this is just a one particular row, for example. Now we are considering n rows, right? So if you think recall how we derive these things, right? So this to the power of -1 will become those negations, okay? And then these take log, well, this 1 by 2 will come here, okay? And because we have n of them here, right? So I will not repeat how we derive this, okay? But when you take a log, the log cancels with exponential. That's why this term comes to here, right? So this is exactly like how we derive things using log before, right? And the one thing you need to pay attention is this. Okay, so although you see a lot of matrices, right? So this is a value, right? Because it determined. This is another value, okay, because it's a quadratic form. Okay, so the log is taking values. Okay, it's really valid. Okay, and yeah. And so ML estimates. Okay, so yeah, next time it rains, we will take 10. Okay, and ML estimates, right? So just like a one-dimensional Gaussian, we say that sample mean is what we will estimate for mu. Okay, and the sample variance is what we will estimate for sigma, right? So when you see those rows, you can compute the covariance of this table and the mu of this table, right? So then that will be the maximum likelihood estimate. Okay, so this will be the maximum likelihood estimate. Any questions before we move on? Okay, then let's move on. Yeah. So if you look at this term here, okay, this term in exponential, which after taking log likelihood, it becomes this term individually. Okay, if you look at this term here, this is called a Mahalanobis distance, right? So it's more like if you think about our regular distance, it's orthogonal, right? So if you have x, y, z, they're orthogonal. But here your x1, x2, x3, they may have some correlation, right? It's not 90 degrees. Okay, so in that case, you need to have the covariance to fix the distance a little bit, right? If it's orthogonal, then you actually don't need the covariance matrix. Okay, so this is the concept. And if you put a constant here, right? So for all the x points, given the sigma and the mu, that those x points that exactly gives you the distance c squared, right? So this thing will give you an ellipsis string, right? In high dimensional space, we call it an ellipsoid, okay? And ellipsoid is in 3-dimensional space, okay? In high dimension, we call it hyperellipsoid, okay? And its shape and orientation of the ellipse, right? So it's defined by sigma, okay? We will see what it means later. We will have a detailed visualization tool to visualize it, right? So, and so Euclidean distance is a special case of Mahalanobis distance. Okay, this is a case when sigma is equal to this thing. So what is this thing, right? So let me activate the pad again, change the mode. Okay. So this thing I is an identity matrix. Basically, you have 1, 1, 1, 1, 1 on the diagonal. The others are 0. Okay. And then if you times s squared, this basically tells you it's s squared, blah, 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 s squared. Okay, this is this matrix, right? And now let's see why it becomes a hypersphere. Hypersphere means a ball, high-dimensional hyperball shape. Okay, a sphere means on the surface, right? So because this is exactly the distance from it, right? So let's put this thing to here. Okay, so this gives you one row vector, right? x1 minus mu1, xd minus mu d. Okay, and times this thing. Okay, you only have diagonals that are not non-zero. Okay, it's squared. Okay, and then you have a column, right? Okay, so so according to quadratic form, the ith row times the the ith term here. Let's see the first term here and the second term here, maybe x2 minus mu2. Okay, you are taking a value here, right? Aij, a12, right? But this is 0. This is all 0. Okay. The only thing that is not 0 is on the diagonal, which means only one x1 minus mu1, and this is also x1 minus mu, right? So this is this square. Okay. Of course, because with this thing, it's a 1 by square. Okay. Right, because it's taking inverse. Okay. So this tells you that this thing is essentially saying that this is array. This is equal to a square of maybe x1 minus mu1 square plus all the way plus xd minus mu d square, right? So this is exactly if you think about this is S squared. This is exactly this. So because this is inner product. Okay. Transpose time. This is inner product. Exactly this. Right. So you can see that this is special case, right? And because this is a constant, right? If you treat this as C squared, like here, right? And you can try to eliminate this by enlarge it as CS, right? C prime squared, right? So this is exactly the ball, right? Hyperbole, okay? Because the shape of x1 minus a plus x2 minus b squared equal to r squared is a ball that is a circle. So that is long A, B, and radius R. Right, so this is really hyperbole. Okay. Any questions? Okay, let's continue. So here, let's think about a simplified form, right? So think about the multivariate normal distribution with two-dimensional space, right? So we are talking about d-dimensional, but let's just consider the special case of two-dimensional, right? So covariance matrix, we can write it like this, right? So here, rho is a correlation of x1, x2, right? So why we can do something like that? This is actually very simple. Okay, so this is just following the definition, right? So we know that covariance matrix, this term is what? This term is sigma 1, 2, okay? Sigma 1, 2 is what? If you look at, firstly, what is rho? Right, rho is equal to sigma 1, 2 divided by sigma 1, sigma 2, right? So that's why sigma 1, 2 is really rho sigma 1, 2, right? In time this. Okay, so this is just a definition. Okay, and so the joint probability, right? So we can write something like this. Okay, why we can do something like this? Let's go back a little bit, right? So if you remember, okay, what should be a term here, right? So let me call out pen here again. If you look at this term here, this is actually, we talked about this, the determinant of sigma, right? So what is determinant sigma? So this is A, B minus CD, okay? So A, B times together is sigma 1 square, sigma 2 square minus CD. CD is rho, sigma 1, 2, rho, sigma 1, 2, right? So everything square. Rho, sigma 1 square, sigma 2 square, okay? And then remember, we have a 1 by 2 in the Gaussian distribution on this side, right? So that's why we finally have this square taken out, right? So, and the square root is this, right? So this is 1 minus rho square, and we take square root also, which gives this term, right? And now we can look at this term, right? This term is even easier because this is z squared x9 and x3, okay? Here we only have x1, x2, it's d-dimensional, two-dimensional, okay? So this is again something similar, right? So here is again, this is sigma determinant. Okay? If you, oh no, so this is actually quadratic form, right? So let me see. So if you look at here, this is the quadratic form. But let's take a look at the quadratic form, okay? Quadratic form is saying, hey, you have x minus mu transpose times your sigma, okay? Sigma is this. So sigma 1 square, sigma 2 square, rho sigma 1, sigma 2, rho sigma 1, sigma 2, okay? Times x minus mu, right? So if you write them out, right? So it's really, if you look at just this term, right? So this is really a column vector of x1 minus mu1, x2 minus mu2, okay? Right. So this is these two terms in the row form. Okay? Then you can see it's really, if you think about the first term and the first row, right? I and j and this ij, then this gives you this term, okay? Right. So after this, because this square is divided, okay? And these thing together is another square, okay? This thing is, right? And if you do this factorize 1 by 1 using the quadratic form shape, you will exactly get this, okay? I will not go into detail. You can make it an exercise yourself. Yeah, so yeah, we are about to take attendance. Yeah, before we take attendance, let's finish this slide and then we take attendance. Right. So here are examples what we talked about. Right. So this is in the case of x and x1, x2, these two-dimensional has no correlation. Okay. In that case, it's a circle. It's a the radius is the same. So basically, if we give it a pen here, we think the center is here, the mean is here. This R1, this R2, right, along X2, okay? And R1, okay? They are the same, okay? This is a circle inside. Right, so the circle is also because of variance. The variance decides the circle, okay? And the covariance decides the shape, right? So the shape is now axis aligned. So for this is not axis aligned, right? So if your covariance is larger, then you are along this direction, which means if your x value is large, your y value is also tend to be large. So you will be along this direction, okay? If your covariance is negative, then you are along this direction, which means if your x value is going to be large, your y value is going to be small, okay? So this will be tilted, okay? And so on the other hand, if their covariance is really zero, right? So again, you are axis aligned. But your variance decides your, your radius, right? So if your variance x1 is larger, right? So then this R1 is larger, okay? So these are the intuition, right? So here each circle means c squared, right? So this c squared is smaller, this c squared is really larger, right? So all these x1 throw into that function. So their probability vector, the probability is the same, okay? So we are talking about something like this. Let me see, we have the shape. We are talking about something like this. Maybe all these x1, x2 values share the same probability value here, and then another is here, a third is here. Okay, so this is how we are plotting that. Okay, equal height, right? Probability height. Okay. Yeah. So we will take attendance now. I see some students coming. Right. So some student coming. Okay, and then we will continue with this. Let me see. I should be logging canvas here. That's not a good sign, right? When I take attendance, a lot of students are coming. Okay. Okay, let's sample a little bit. Okay. Gahada.
Yes, I'm here.
Okay. Pritesh.
I'm here.
Okay. Chunyao. Chunyao.
I'm here. I'm here.
Okay, got it. Nikhil. Nikhil.
I'm here.
Vikram.
Yes, sir, I'm here.
Okay. Pat. Pat.
Yes, sir, I'm here.
Okay.
Yeah, I'm here.
Oh, got it. Okay. Lina.
Yes, I'm here.
Okay. Prithvi. Prithvi.
I'm here, sir.
Am I pronouncing the name? How do I?
Prithvi.
Prithvi, right?
Yes.
Okay, got it. Medit.
Yes, I'm here.
Okay. Peidali.
I'm here, Professor.
Okay. Zhiying Lu.
Yes, I'm here.
Okay. Revent.
I'm here, sir.
Okay. Nishant Paba. No. Let me see. There's a chat. I didn't call the name. I think. So let's go back. Okay. Saidipa.
Yes, sir.
Okay. Clark Ren.
Here.
Okay. Boniface Singdala. Boniface Singdala.
I'm here.
Okay. And Kona Susik. Susik. Kona Susik.
I'm here.
Okay. I think that's the end almost, right? So Amulia. Amulia. Oh, I see another chat. Just one. Okay, I see Amulia here, and let's get another one. Maybe Ran Yan.
I'm here.
Okay, Vanka. Vanka. No. Latif. Latif. No. Okay. Garat.
I'm here.
Okay. Let me see. Deepak. Oh, Latif actually. I will go back to chat and good. Okay. Chat.
I'm here.
Okay. Let me go back. I see a few students chat. If you can use a microphone, that's the most convenient. Otherwise, I have to check the chat. Deepak. Let me see. DIPAK. I think I called.
I just
Yeah.
was out there, so you took my name or I forgot.
Oh, what? Can you repeat? I didn't get it.
Deepak. Did you
Deepak.
type my name?
Is this your name?
Oh yeah.
Yeah,
Okay.
I probably didn't call your name because I sampled a little bit. Okay, because of time limit. Yeah, it's okay. Let's. Yeah, because the next time if I didn't call your name and you chat, then that could mean that you just joined. Okay, so that's a little bit worrying. Okay, but this time I will just let go. Right. Okay, let's continue. So if xi are independent, right? So and the off-diagonal entries, right? So then will be 0 because if xi are independent, which means all the columns are pairwise independent, which means sigma ij should be 0. Okay, so yeah, it's not a good sign because after tangent, some students just disconnect. And so this is 0, which means in your covariance matrix, as long as your ij is not equal to each other, it will be 0. Okay, this will be 1. This will be non-zero. Okay, then in that case, we can factorize them. Okay, we can factorize them into this shape. So why? So one reason is this. Okay, so if you look at the covariance matrix, right? So this may be sigma 1 square, this is sigma 2 square, right? A sigma d square. Okay, and then determinant of a diagonal matrix is equal to what? Is equal to product of the diagonal elements. Okay, a sigma 1, a sigma I square. Okay, and if if you take standard deviation, you take a square root, you get this. Okay. And it's similar if you consider quadratic form, right? So you have this thing, x1 minus mu1, x2 minus mu2, etc. Okay, and this is the column, right? And then you have the quadratic form. Okay. And if you have the quadratic form, then if you factorize them out, it's really not, any elements that are not equal, right? I and j are not equal, not squared. They are 0. Okay, only when x1 minus mu1 times sigma 1 squared. Right? So yeah, here. Okay. By the way, this is because this is negative. Okay, inverse. That's why it's about. Okay, and if factorize them like this, you will get this. Oh, here we use another theorem, right? So if you have sigma 1 is a diagonal matrix. Okay, but if you take the inverse, it's 1 by each diagonal element. It's 1 by sigma 1 squared. Okay, so these are actually what you should learn in matrix. Linear algebra, right? So if you have diagonal, this is A, this is 1 by A. If you tie together, it will be identical. Row times the cost of A times 1 by A is 1. Okay, so So yeah, I hope you can get this. I do see another chat. Yeah, I see Nishant Pal. So can you explain a little bit why you were not here when I take attendance? Right, so because I see 2 students leaving, so maybe I take it you would leave. Right, so I want to make sure this attendance is not just a, it's to faithfully reflect whether you are in the class and listen to majority of the class. Okay, if you want to take a leave, as we said, if you ask before that on Canvas, that will be allowed. You need to send me email before the class, not after. Okay, or not in the middle. Right? Otherwise, if you just join and take attendance and leave, you will not count it. Okay. All right. So, and so here you can see that we are divided by sigma, right? Because the diagonal matrix, sigma 1 squared, sigma 2 squared, sigma n squared, right? So if we think all the sigma are the same, so basically all these things become the same. Okay. This is all sigma. This is all sigma. Then this becomes constant, right? And this becomes constant that can take it forward, right? Becomes 1 by sigma squared. Then you are really just comparing this thing, which is exactly the Euclidean stuff. Okay. Well, on the other hand, if you do have different sigmas, right? But this is product of all the sigma is still the constant, right? So you consider weighted Euclidean distance, where the weights are given by 1 by sigma, okay, 1 by this, right? So here's the logic. Okay, so now, so far we are only talking about the probability. Okay, so Y is P. Okay, Y is P. Now let's consider Y is class. Right? So basically we're talking about posterior probability. Right? So if you if you see X, how likely was CR? Right. So posterior probability is composed of this class conditional density function, or we say the generative probability times the prior. Right. So let's first look at this term. Okay. And this term, as we said, is equal to this. Right? This is just because we assume it's Gaussian distribution. But here we are assuming something like this. Right? So we're assuming generative probability, which means if you are belong to class 1, it's a Gaussian distribution associated with class 1 is mu1, sigma 1. Okay? If you are talking about class 2, then you have another Gaussian distribution, mu2, sigma 2. Okay? And although, let's say you have k classes, then you have k sets of those kind of Gaussian distributions. Okay? Once you are pretty sure this data is coming from this class, then you're sampling from here, and then you are using the class parameters, and this general probability is equal to this. Okay. And as we said, the posterior, which is a discriminant function, right? Which class is highest, right? This I class I, okay, is equal to the general probability plus the prior after you take log. Without take log, it's product. Okay. And so we will put the prior here. And this thing is exactly what we see before, right? So taking the log of this, gives us this, right? And the parameters can be estimated separate for each class, just like what we saw before when in the univariate case, okay? And actually, not just that. Actually, it's kind of similar to the univariate case in the sense that, your mean for each class, your sample mean. Your mean for covariance matrix for each class is also your sample covariance matrix. So what do I mean here? You think about a table, okay? You have x1, x2, blah, 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 okay? And then you have a class, okay? Maybe you have 3 classes. This is 1, 2, 3, 1, 1, 2, 3, 3, okay? Something like that. Right. So when we talk about the first class mean, right? We just pick out these rows. This guy's row, this guy's row, okay, and this guy's row. All the data points that belong to class 1, right? And then using these as a table, we compute their mean and their covariance matrix. And let's say we have 3, so this will be 3. Because this is an indicator variable, the others will be 0, okay? And this is also indicator variable. If it's not belonging to class 1, this thing will be 0, okay? So this basically is saying this. Right. Any questions? So this, we will derive this, by the way, okay? We will derive this. This is a maximum likelihood estimate. okay, in high dimensional case, which is a little bit more complicated. So first you accept what we are talking about here, right? And this is a prior, by the way, right? So this prior is a multinomial distribution, right? So if you just have y and we see these, the probability really something, right? For example, for class 1, it's really equal to, you know, this is R1 is only for these R1, right? So we have all others. And this n, maybe we have 10 of them, then 3 by 10. Okay, this is 30% your class will want to see. Okay, and maybe for 2, it's a little bit less, maybe 20%. Okay, so it's the same. It's just like in the univariate case, your prior is estimated as a multinomial distribution from class column. Okay, this is the maximum likely estimate. And for the general probability, now it's high dimensional case, but it's still the same, just like before. Okay, the difference here is this. Okay, let me see whether that will be clearer if we go back to your previous. So this is 59. Okay, let's see in the univariate. Let me see where it is. 59. Yes, this is the previous page we are talking about. This, right, so previous page is one-dimensional case, right? So just x1. In that case, this is what? This is one value. Okay, this is another value. Okay, scalar. Okay. Now in our new case, okay, so if we go back to 59. Okay, yeah. Here it's kind of different. Okay. This is a vector of d-dimensional. This is d by d. Okay. This is a d-dimensional vector of your data table. Right. It's a row. Okay. And this is what? This is a autoproduct, which is the matrix. Okay. Any questions? Okay, if not, so you can see this is auto product of that's 3 items for your class 1, and this is by 3. Right? It's exactly following the covariance matrix definition. Okay. Now let's derive this. Okay, why this is a maximum likely estimate? For this, it's pretty obvious, right? This is still one dimension. Okay.
Remind me what MI and SI are, please.
What?
Remind me what MI and SI. What are those?
Oh, MISI is a sample mean and a sample variance. Okay, this is the distribution, but when you see the data items, right, so see the table, their mean and the variance may not exactly be this. Okay, it's a random sample, right? That will be close, but not exactly. Okay, it's estimated from the samples. Is this okay?
Can you say that is the weighted mean?
No, it's not what you mean. For example, I just talk about the example. This is a class, okay, and you have class 1, 2, 3, 1, 2, okay, right, and then you have maybe the first data item is Q1, these attributes, okay, this is X2,
Okay.
this is X3 attributes, okay, this is X4 attributes, this is X5 attributes, okay. So basically, this is saying that this is indicator variable. Let's say R1. R1 is saying whether you belong to class 1. This is 1, this is 0, 0, 1, 0. It's okay, right? So if you look at this bottom is 2 because you only have 2 class 1.
I thought the R is the weight of the variable X.
No,
Can't we say?
indicator variable. Okay.
Okay.
Yeah. So this is basically saying this is x1 plus x3. Okay. So only these 2 are belong to class 1, right? The others is there. Right? And similarly, look at here we have five data items, right? N equal to 5, and only 2 of them are 1. Okay. If you sum all the column is 2, right? Because only 2. Any questions?
Okay.
Yeah, I hope this example works. This is a covariance matrix because you still take a derivative n equal to 2. Okay, but this becomes a, using the d-dimensional vectors to compute this. So this is the okay, cool. Any questions? Yeah, if it's not clear, just let me know. Right. So what is this? Oh, okay. So I think we should go to the derivation. Just let me pull it out. Yeah, it's in our lecture note, and it's here. Right, so the last one. Okay, so I think I need to call out the annotate. Yeah. So this is exactly like before, right? So we have n items. This is nth row, right? Here we use small n, min I. Okay, so altogether we have n data items. Okay, and this thing, okay, this thing have a constant here. Why? This is because if you go back to our formula, so this is the constant. Okay, 2 pi, right? We have the negative 1/2 log sigma, right? And this quadratic form, and then prior. Okay. Okay, so this is okay, the quadratic form, right? And prior and the 2 pi thing goes to the constant. Okay, otherwise it's the same, right? Because for different classes it's the same. We don't care what's the difference. Okay, for any class, class 1, class 2, class 3, they are all adding the same thing. Okay. Oh no, it's not, right? So it's actually not that simple. Okay, so it's not relevant class. Okay, it's still the general probability. Okay, sorry, my bad. Okay, there's nothing related to classification yet. Okay, it's just the probability. Okay, these are just constant. Okay, and when you take a derivative to, let's say, mu and sigma, they don't play a part there. It will be 0. So we can simply write it constant when we take a derivative. Okay. Next is taking its derivative with respect to mu, right? And then with respect to sigma, okay? And set to 0. Just like, the Lagrange method, right? So I'm not Lagrange, okay? So the method we talked about, okay? Just stat all the parameters to 0, okay? After taking derivative, right? So lowest, this is where you get the optimum, okay? Right, so let me see. So it's the lowest point along every dimension, right? So along all parameters, it's 0, that is the lowest point. Okay. Now, firstly, we want to take a derivative of this to mu. And keeping in mind, mu is a vector. Okay. So how do we do that? Obviously, this term is gone. This term is gone. Okay, because they don't have mu. Okay, mu is contained here, right? So what we will do is using chain rule. The first thing is we consider x minus mu, right? We call it y vector. Okay. So now it becomes y sigma y, right? So this is transpose. This is a quadratic form, and we have seen that in quadratic form what we have is sigma y, 2 sigma. Why? Because this is symmetric. Its inverse is also symmetric. Okay, symmetric matrix inverse is also symmetric, right? So that's why you can have 2 sigma y. If it's not symmetric, you have to write it like a sigma negative y plus sigma negative transpose. Okay, but now we can simply write it 2 sigma. So here we have 2 sigma minus times y. Y is what? Y is xn. Okay, then this is y, right? So then according to chain rule, we need to take a okay. When you take a mu, you know the coefficient is negative, right? So you just add negative. Okay? And then you set this derivative to 0. Okay? Set it. And when you set to 0, this constant is gone. And so the left hand side becomes 6. Okay, so let me see. I forgot the summation. The summation should be okay. So ultimately, what we have is okay. So summation of I, maybe instead of using n, let's use I. Okay, and we know that there's a sigma negation. So this thing is okay, and the summation of xi, because sigma negation is a constant, not relative. We can take it out. Okay, and equal to 0. Okay, and this term can be further, and this thing is gone because it's it's equal to 0, and this is constant is gone. And if we further factorize this becomes sigma I xi equal to sigma I mu, right? Mu and sigma. But the sigma I mu is not relevant to I, and we have n of this summation. So it's n. Okay? finally this mu is equal to 1. We divided by 1 by n. We get this sample. Okay. Any questions? I hope it's fine. Okay. Yeah. So keep in mind these are all vectors. Okay. So now next task we do is this. Right. So we need to take a derivative sigma. Right? So this is a little bit crazy here. Right? So we have sigma here, inside determinant, inside log. Okay, this is sigma which has an inverse. Right? So it's a little bit crazy. Okay, and inside the projective field. Okay, so yeah. So in order to make it work, we need a so-called trace tree. Right? So why it's called a trace tree? Because we know that in the derivative we have a section called a derivative trace, right? But here we don't have trace. Okay, we don't have trace. Right? So we need to create some trace, then we can take derivative further. Okay, otherwise we cannot find a formula for that. Right? So how can we do that? So idea. So first let's take a look at what is trace. Okay. So who knows what is trace?
Diagonal.
Diagonal element. Okay. Yeah. Sum of diagonal elements is trace. But trace has some nice properties, right? So for example, you can swap them. Okay. So AB and BA are traces. Okay. Keep in mind that trace only works for square matrices. Right? So basically, A and B are both n by n. Okay. And there's another nice property here, which is very important. Okay. So this is a generalization. This can generalize to here. This is called like a circular rule, which means, for example, if you have A, B, C, right? And then now, if you move A to here, okay, like A, B, C, you move A to here, okay. That's it. A and put it here. BCA, the trace is still the same, and you can further do something. So, for example, you can move B to the front, okay, B to here, and then you move this B here, okay, and this becomes this, okay. So it's like it's a circular way, okay. Of course, there are some restrictions. So you know, CAB is, but the CBA is not, okay, because you cannot move from like a circular way and recover. Okay, so there's a circular rule. All right, so this is one thing. The second thing is trace. The trace trick is just saying that if you are scalar, right? So you are scalar, then A is equal to trace A. Okay, right? Because your A, you are one dimensional, right? Your diagonal is A itself. Okay, so this is the trace trick. So let's use a trace trick to see how to do this. Firstly, to use a trace trick, you should observe this. Okay, this thing is what? This thing is a scalar or vector or a matrix. What is this? Who can tell me? Let me find people to ask. Okay, Sami, what is this?
I think it's scalar. Sure.
Yeah, it's a scalar, right? It's a projective form. Finally, give you a scalar. That's it, right? So A equal to trace A. Okay. So that means we can freely add a trace outside. Okay, outside, and then we can move around. Right, we can move this thing to this side. Right? So this thing is moved to this side. Okay, so this is the trace tree. I hope you can see. This is a scalar, so add a trace is free, and then we move this thing to the front. Okay, and after that, so we'll just go through some complicated stuff once, okay, because this is not required, okay, unless you want to delve deep into machine learning. Okay. But let's tell you how to do these things actually if you want to delve deep. Okay, and yeah, so you use proportional, so we can. Okay, it's not actually proportional. Proportional should be p, right? Because this is proportion means a time something. Okay, so this is actually just to say we are ignoring constant. Notation not accurate. And now what we can do is, you know, this thing is a constant, right? It's relevant to I, okay, and right. So we can move the I inside. It's the same. This is actually using another trace rule, which is actually quite intuitive if you just think about diagonals. So it's using this. Okay, this is 15. Okay, summation you can take it inside. So this summation you can do it inside. This thing is constant, relative xn, right? Index you can look up, right? And now we are ready, a little bit more ready to take derivatives. Right, so we have sigma right here, we have sigma here, we take derivative for each term, and we see what we get, okay? So the first, so here we already give you some conclusions, right? So we are giving some hint, matrix suitable 57 and 62, right? So let's take a look at what I, okay? Now what we are doing is take a partial derivative, partial sigma, okay? So the first thing that is a little bit headache is this determinant, right? So we want to take a derivative sigma, but sigma has a determinant, right? So what do we do? Okay, right. If you are not good at mathematics, what do we do? Okay, we go to matrix workbook. Section 2 is derivatives, derivative determinant. Okay, let's see here, right? And you want a log. Okay, if you come back, you have a log before determinant. You find this thing with log. You can look it up, and I think, are we passing? Let's see. It's already 2.3, 2.2. Okay, so it's this one. Okay, I hope you can see. Right, determinant and log. Okay, of course we have absolute value because maybe determinant can be negative. So, but for our case, we don't need it because it's a covariance matrix. Covariance matrix determinant is always positive. Okay, so we don't have the absolute value. So this absolute value here is the determinant here, det here. Okay, so this gives what? This gives us what they say is if you want to take a derivative, it will give you something like first as this matrix you take partial derivative. First compute its inverse, then transpose it. Okay, and we often write a shorthand notation called the inverse transpose. Okay, it means inverse and transpose, or transpose inverse. So they get the same result. Okay. Let me see. Oh, I'm using the wrong path. Sorry. Okay, so if you come back here, this is saying that if you take a derivative this term, right? So what it will give you is this. The constant is still 0 by 2. Okay, but this thing will become what? Okay, determinant x lowing becomes x. Okay, so here x is sigma. Okay, this term will become sigma inverse. Okay, so this is what inverse transpose. Okay, right. So this is what we have here. Now let's look at the second term. Right. So second term is also a little bit heavy. Right. So remember we use the trace trick. Okay. So we use the trace trick. Right. So then we probably want to find the derivative of trace. Okay. So we'll directly go to 63 to save time. Okay. So let's go to 63. Yeah, you can see here it's run to trace. Okay. 63 gives us this thing. If you look at it. Is this one? Okay. Yeah. So here you can see we have x inverse times b, take derivative x. Trace it before, right? We do have additional a here, okay? So we have x here, right? So x inverse is sigma inverse, okay? And b is this. Remember, this is auto product. This is matrix, okay? And outside we have a trace, okay? Everything looks nice except we have an a. Right. So here A can be identity matrix, right? We just replace the identity matrix. So this becomes gone. Okay, this A is gone. Right. So what we are saying is that using this toolbox, you can derive if this is gone, this identity matrix, it's equal to X inverse B identity matrix X inverse. Okay. And transpose. Okay. And then using that part, you compare, you replace X inverse with sigma inverse. Okay, right, and then you will derive this. Okay, and you see this here. There's an and here, right? So here it's a B is this term, right? It's still here. Okay, right, and then this one sigma inverse will be cancelled. Okay, one sigma inverse. Another sigma inverse will go to the other side and it becomes not inverse. Okay, I will leave the rest of the derivation to you because of time limitation. Okay, you can derive this, right? Just follow what we discussed, and you will be able to derive this. This is sample variance. Okay, so this derivation actually applies also to like a Gaussian mixture model. Okay, we are also doing something similar, but there we have a softer, it's a little bit different, but the derivation basically is the same. Okay, yeah. So that's it for high dimensional Gaussian. Okay, so why we still have the same conclusion. Let me see where are we. Let's do these numbers. Right, so especially we are deriving these two. Okay, for each particular class, C1, why we are just taking sample mean and sample variance. Any questions? Okay, let's continue. I think we are a little bit out of time, so we will be a little bit faster. Okay, now that we know that the maximum likelihood estimate is to plug in so the sample mean and sample variance, right? So then, let's come back here. We know that previously we have formula something like this, right? Now we just put sample mean here, sample variance here, okay? And this will give us this, right? So M and SI, right? And this is prior, and 2 pi is a constant gone, okay? Because for any class, this part is constant. They don't impact their relative order, okay? And now let's continue here. Yeah, let me see. Here I should use a slides pen, okay? So here you can see that what we care about is really X, okay? The input is X now, okay? So they have several terms. One is quadratic term because X times X, right? Okay, and one is linear term, right? So if X times Mi and it's a constant, it's a linear term. Another is something irrelevant to X, which becomes to the constant, okay? Goes to this constant, right? So let's take a look at how to derive these things, right? Maybe I need a little bit more space, so I should go back one step. Okay, let's be here so that we can do some derivation using the space down there. Okay, so now let's look at this term. Right. So this has 4 terms. First is this thing times this thing times this thing, which gives you this thing, right? And you can also do negative mi times this thing times negative mi, give you this term, right? So the trickiest thing is x times this thing times negative mi, which is negative x si negative 1 mi. Okay, and then we have this negative mi times s times x. Okay, so this is a negative mi transpose. Right, so this has a transpose. Okay, times si times x. Okay, so these two are actually the same thing. Okay, that's why we just twice this term. Okay, so how to see they are the same? We just take a look at what are they? Are they scalar? Are they vector? Are they what are they? Sami?
I'm not sure, sir.
All right, so let me tell you. Okay, so this is row vector. Okay, this is square matrix. Okay, this is mi is column vector. Okay, So row vector times the square is row vector. Row vector can call it the dot, okay, which is the vector scalar. It's okay. So if you replace mi with x, it's a quadratic form, right? So, but if you use other mi instead of x, it's still the same size. It's not a quadratic form x, but it's still the same size. Okay, these are scalars, right? And for scalar, we know that A transpose equal to A, right? So because it's just a one by one. Okay. So now let's take a look at what's a transpose, right? Because transpose itself. Okay. So mi is I transpose. So transpose, you know, you will go this direction, right? So this becomes x transpose. Si negative transpose. But Si is symmetric. Okay, it's a sample covariance matrix. Let's do the same. Okay, Mi transpose cancels. Okay, so this is this term. This term is exactly this term. So that's why we have to. Okay, so this is how we derive this. Any questions? Keep in mind we use a lot of inside data. This kind of shape, right? Quadratic form kind of shape is the scalar. Okay, that's why we can use a trace trick. We can also use this trick, transpose trick. Okay. Yeah. So let's come back. Now, finally, we can write it as a quadratic function of x. Why it's quadratic? Okay. Let's take a look at it. So firstly, this term is quadratic term, right? This is a quadratic form, ax squared. Okay, well, this is a, this is x squared. Okay. And you know, so this is the coefficient is here. So you know, we can put it here to say this is a coefficient of the square term. Okay, right. And if you look at the linear term, so linear term is if you have x. Okay, right. And again, we said this thing is equal to mi is I. Right, so you can also consider this as a coefficient, right? So, so basically they are the same. Okay, in the product, wi times x is equal to x times w. Okay, so you can write it differently. Also. Okay, so this is wi basically. Wi times in the product x and wi equal to wix. Okay, so don't think it's a mistake. Okay, so this term is this term, right? Because this is -2 and then -1/2 cancels, right? And finally, we still have some constant term, right? One constant term is this term, which is here. Another is a prior, because we are comparing posterior, which is here. And we also have a constant contributed by this times this coefficient. Okay, so this is how we can see that it's a quadratic form. Okay, and the coefficient has these. Keep in mind these are constant, right? When you have the table, you know the sample mean, sample covariance. Okay. And you know the prior because you have the y column, okay? And then once you compute these, you get this quadratic formula for your discrete function, okay? When you plug in a new data point, you can see G1, G2, G3, which is highest. If the G2 is the highest, then you belong to class 2, right? So this is what we are talking about. And this is really a quadratic shape. Any questions? If not, we will continue, okay? Yeah, here is example, right? So if you have two Gaussian distributions, these are the PDF of C1 and C2, right? And then after you do the posterior, right? So this is you know, this is the posterior, okay? If you see X, how likely you belong to CI? If this is a CI, this is generative, which is a Gaussian, okay? And then you will see that it's some shape like this, okay? Why? Because one Gaussian may be something like this, okay? Another Gaussian may be something like this, a covariance, maybe this is more positive correlated x-linked, this is negative correlated, okay? And the boundary where, you know, the probabilistic function are equal along this line, okay? And on the left-hand side of this line, you belong to this class. On the right-hand side of this line, you belong to this class, okay? This is the visualization. Any questions? Okay, so let's continue then. Another way is we just like before, right? We talked about shape, right? So, but what if for each class they have SI, then the shape could be quite irregular, okay? Right, so the covariance for this is along this direction, another is along that direction, okay? But what if we have a nice property that all of them share the same covariance matrix, right? So what does it mean by the same covariance matrix? That means, let's say you have a table, okay? And this is a class, 1, 2, 3, 1, 2, right? You don't care about C, right? You just compute the covariance matrix of the whole X matrix, right? And it's something like a divide by 1 times the N matrix summed together, right? One for each data term, each row, okay? So actually we can show that we can compute using each SI that we already computed, okay? And apply here, estimated. So why this is the case? Why this is the case? Right, so let's go back to a prior page. Let me see where it is. Right, let's go to here. Right, so we just talked about we want the overall S, right? Overall S should be equal to 1 minus N sigma L, right? So it should be this XL minus N, XL minus N transpose, right? So this is the overall sigma, right? So why this equals to summation of L I, this should be I, by the way, okay? This index is not on the rows, it's on the class. Okay? So why this is I, right? So this thing times this, right? So this is very simple, right? Because this cancels with this, okay? So the bottom is really divided by N, just like before, okay? Now, these are for that particular class. Let's say if we have 1, 2, 3, right? So for class 1, only 2 of these items are non-zero, so contribute. For class 2, you contribute this. Class 3, you contribute this. So altogether, you really contribute this, okay? As a top, right? So they are really equal, okay? So there's the relationship between them, something like this, right? But you can directly compute the X, ignore the Y. That's the same, okay? In that case, the discrete function will not be quadratic anymore. It will be linear. Okay? It's still quadratic, but it's a special case of quadratic, which will be linear. Why? Let's go back to this function again. This is the boundary, right? So this function, okay? You think about it. Now for G1 and G2, okay, G2x. Does this term play a part anymore? The answer is no. For the same X, your WI is the same, okay? It's the same S, right? So this term is the same when you compute G1x, G2x, G3x. So the relative order really decided by this term, okay, which is linear, okay? The quadratic term is gone. Any questions? If not, let's continue, okay? Yes, this is the most mathematical lecture here, okay? So these are important for you to get familiarized with, at least get familiarized with those kind of operations, right? So not too bad, okay? Later when you see something, you're at least more familiar with this, okay? So here, we only have 2 terms now because the quadratic term doesn't play a part. S is the same X, okay? X transpose as X. It's the same for all classes. So we only have 2 terms. Right? If we pictorially write this is actually a linear classifier, right? It's a linear separator, okay? Right? It's no longer some curve, okay? And again, it's linear because the covariance is the same, which means they are along the same direction, okay? So they are along the same direction, right? So they are along the same direction. Covariance is the same, okay? And we can further simplify it a little bit, right? So we consider naive Bayes classifier, right? Naive Bayes classifier is actually a special case where all variables are independent, okay? So that means, besides the diagonal elements, Ri 1, 1, 2, 2, 3, 3, right? Sigma 3, 3, sigma 4, 4. If you have sigma 1, 2, it should be 0. Okay. If that is the case, we know it's independent, right? So if it's independent, we can factorize, right? So let's say in your table, you have C1, how likely will generate the third feature, the second feature, the first feature, right? So they are independent. It's not joint. You can take the product. This guy to this guy, this guy to this guy, this guy. Take the factorize them out, okay? And if that is the case, I think. So, each one is a univariate Gaussian distribution, right? So it's kind of something like this, right? So why? Remember, if you think about the one dimension case, right? We don't have this, okay? So exponential, this one particular case is exponential of a particular Sj with xj minus mij, okay, right? And this is a product of it, right? And product of exponential or something, essentially, if you just look at exponential, it's summation of the other terms, okay? Right, so when you are up to exponential, that's why we have this term, summation, okay? I hope this is okay. Right, so this basically gives you the weighted Euclidean distance because because you have the diagonal elements are still different. Okay, so you have it's like Euclidean distance but weighted. Right, it's already simplified a little bit. Okay, so this will be looking like this because if you have no correlation, right? It's x large, y not determined. Definitely larger, sometimes larger, small, then it's offset. So your axis aligned. This is aligned with this, it's aligned with this. Okay, so there's no preference there. Okay, and let's continue. Yeah, let me get used to a little bit of this. Okay, yeah, diagonal. So finally, we think about the diagonal elements are all the same with the same variance. Okay, with the same SI. Okay. This finally will become the weighted Euclidean, right? So because the previous sum we have different SIs, now we have the same SI. Okay, so now if you can take them out, it becomes a Euclidean distance, right? So this becomes the nearest mean classifier. The closer your mean is, the better. Okay. If graphically we can call it the template match, right? So whoever is closest, you go there. So this is like the Varroy diagram we talked about earlier, right? So it's not only axis aligned, but the radius are the same. Okay. Right. Of course, you might think, hey, this is not exactly cross the origin, right? So why? Let me see. Why I cannot do this? Yeah, because we still have this term here. Okay, it's not exactly passing through. Right. And finally, let's take a look at the model complexity. Let's just look at the covariance matrix. Okay, don't look at the mean. Okay, mean has additional d dimensions. Right. If you assume everyone is shared the same covariance matrix and it's spherical, which means the diagonal variance are the same. Right. Then you only have one parameter, which is S itself. Okay. And next, you assume that it's shared and not correlated, right? The correlation is 0 for xi, xj, and xi, xj, right? So then you only have diagonal elements, which there are d diagonal elements, okay? Further, if you assume they are still sharing the same covariance matrix, but then they are not totally, it's not a totally uncorrelated, right? So different dimensions may correlate, okay? Then you have this, right? So why we have this? Because the covariance matrix is d by d, okay? But when you store them, it's a symmetric matrix, right? So if you store here, you can immediately get this, right? Swap ij, you get the value here, okay? So only need to store these values, okay? So how to compute this, right? So we know the diagonal, there are d elements, okay? And the corner is one element, then this is two elements, right? If you compute this, is 1 plus 2 plus all the way plus d, which equal to this value, right? And remember, this is always a square matrix, right? And finally, if you assume everyone has a covariance matrix, right? You have k classes, right? So then you have time parameter k here. So there are a lot of parameters here, okay? So depending on how many data you have, you can use, if you have lots of data, of course, you can use the most complicated data parameter, right? If you only have 10, maybe the best way is the first, okay? So model complexity increases as we make it more general, okay? But but the bias will decrease. But if you don't have enough data, right, your variance will increase and it will overfit on your data, okay? Actually, I think it's underfit, right? So because you don't have enough data to train, okay? And regularization, right? So you can add regularization. One way to add regularization just using a simpler model, right? So it's like you want a strong bias. You want to increase a little bias, right? So it's okay. I use simple model. The bias a little bit large, but I want a trade-off to avoid my model don't generalize. Okay. And finally, we will quickly go through a few other high-dimensional multivariate data distributions. Okay, the idea is very simple. So previously we say that it's the zero-pointed Gaussian, right? So we can also have like a Bernoulli, right, which means 0 or 1 by binary distribution. Okay, so the only difference from the previous Bernoulli distribution is that now we are considering here we are considering naive Bayes in some way. Okay, so every xij's, xi and xj are independent, right? So we are talking naive Bayes. If this is the case, we can directly take the product of their probability density function. Okay, and where the j's dimension is new addition. Okay, so j's dimension is for the j's attribute. Right, previously we only have one attribute when we derive this. Okay, and because of this reason, when you compute, right, so you take the log, this will become summation. Okay, and you do have an additional summation over j, right? But when you take a derivative, it doesn't matter, right? So when you take a derivative Pij for a particular I or for a particular j, right, the other j values are gone. So when you do the maximum likelihood estimation for a particular Pij, where j is fixed, right, other j's doesn't play a part, which means other columns doesn't play a part. So using the same derivation, you can still get this. Okay, it's sample mean is a P. Okay, and this also holds for multinomial distribution, right? So I will leave it to you. Okay, it's still the same because we are assuming naive Bayes, right? So we just have another product dimension of j. But when we take a derivative to Pijk, where j is a particular fixed value, the other terms in the summation doesn't play a part, right? So our derivation is exactly the same. Okay. And finally, let's take a look at the multivariate linear regression. Okay, so remember we previously considered univariate, which means we only have one x value, x1, but we can have x1 square, x1 cubic, etc. Right? So this is a polynomial regression. Right? Now we consider linear regression. This will be in our assignment. Okay, but we will ask you to do it linear regression using matrix form. Okay, multivariate calculus. Here we will do element-wise calculus. Right. So here we assume that each attribute value is associated with a weight. Okay, of course you have a bias, right? It's like a weighted sum, right? This is often used in, let's say, linear support vector machine. Okay, and this is a white noise. In regression, remember we have a white noise associated, right? So, and if this is the case, we can compute the error function, right? We show that this is the mean square error, right? So this is your estimation, your real value minus the estimation. That's the estimation of this R. This estimation value. Okay, R hat. Okay, and you want to minimize this error function. Okay. The derivation is exactly like before. So if you minimize this, it's equivalent to maximum likelihood estimation before, right? So the derivation is exactly like before. Let me explain why it's exactly like before. Okay, like the polynomial regression for univariate case. Let me go back there. So this is page 70. Okay, let's go to the univariate regression place. So this is our previous case. We only have one particular x1, but we have to the power 1, to the power 2, to the power k, right? Xk, right? And we have this d and r, right? So what's the difference here? We still have this w, right? So the difference compared with this page, 70. Compared with this page, next page, is that now x1, x1 squared, x1 to the power d is replaced by x1, x2 to the power xd, right? It's linear, but different column values. Okay, it's not the same column values, take the power or something. Okay, so the derivation is exactly the same otherwise. Okay, so except that previously this is x1, this is x1 squared, this is x1 to the power d. Now we take different column values here. Otherwise, it's the same. Okay, and you can also factorize into this kind of shape, and you can show that it's pseudo inverse, right? And this factorization, that x transpose times x is equal to this thing. Last time we also show how to do that. This is not easy. Okay, and in the assignment one, written assignment 1, you will see that using matrix notations, right? The linear and quadratic derivatives we taught before. Okay, you will easily derive this without much difficulty. You don't need to be able to see that, you know, this matrix is actually this thing transpose times x, okay? Outer product or something, okay? So that's why you need to know a little bit more high level linear, you know, the derivative in high dimensional space, okay? That will help you a lot. And finally, I think that's the end. Okay, so finally, I will use maybe 1 minute. Okay, so high order variables. Okay, so think about your data is something like this, right? So you have circle, 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 circle here. Okay, and then you also have some other data items like something like this, right? So let's say the tick is a negative class, circle is positive class. Then you want to have a circle around. Okay, right? So to separate them. Okay. And now if you have a linear classifier, you can never do that, okay? Whatever you do on each side, you will have ticks, okay? You will have negative class, right? A way to do that is you still use these two features, x1 and x2, right? But you create more features from them, right? x1 square, x2 square, x2. With these, actually, we'll be able to use a linear function over z, right? w1, z1, w2, z2, w5, z5. You will be able to separate the original space using a circle, right? So because, you know, the circle is really something that we said before. X1 minus a square plus x2 minus b square less than equal to. Okay, it's really some shape like this. But if you factorize it, you can really use the z1, z2, z3, z4, z5. It's a coefficient you can compute. Okay, and it's a let me see why I cannot find my mouse. Yeah, I think, yeah. So you can see that if you factorize them, right, you have x1 square term, you have x2 square term, you have x1, x2, but here in this special case, you don't have x1, x2, right? But if your AB is shifted a little bit, right, so it will have x1, x2, right? So in any case, you can represent this circle shape to separate these two using a linear line in this space, okay? Because in that space, it's just W1 times X1, W2 times X2, W5 times X5. And if it's minus R equal to 0, that's a line, okay? If it's less than R, then it's on this side of the plane. Larger than R, it's on this side of the plane, okay? Yeah, so we will see more about this in SVM models, okay? Yeah. Sorry for delaying a few 1 or 2 minutes. Okay, so that's end for today. We finished this slide finally. Okay. And yeah, okay, thank you. Next time we will talk about logistic regression. And if you have questions, feel free to send me email, and you can also ask me right now.
Thank you, sir.
You're welcome. Oh, for the next assignment, I think we will post them later this week or by early next Monday. Okay, we will see. Maybe later this week. It will be a written assignment instead of hands-on, by the way. Okay, if you have no questions, I will get offline. And I think one TA missing, you know, cannot attend this week's TA office hour. I'm not sure really. If you want, you can confirm with him. Okay, so if you have any questions, you can send me email, and we can make one to do QA directly. Okay. And from next week on, I think the TA office will resume. Okay, I think July is still doing the normal TA office hour. Okay. For the project, I'm still waiting for the TAs to get the final data to me, and we will offer the annotation, you know, the object detection data set for you to use some particular specified model, a list of models that you can choose, and try a project, like a hands-on project. Okay, but you can choose your own project, but you need to discuss with me because, you know, as I said, we need approval these days if you do projects not within the scope of our provided list. Okay, we will release that later this month. Okay, so that you can start preparing. And because some students before reach the same project for multiple courses. Okay, so that's why the department has some new rules that we have to do the checking. Okay. I hope I answered the one student's question. So because he asked me privately, so I just yeah. Yeah, if you have any preference of what you want to do, just email me. Okay, but it has to be related to what you learn in this course. Okay, or a little bit more difficult is fine. Maybe something deep learning is fine, but not simple scikit-learn library code. Okay, so at least you have some more sophisticated component, like a particular application, right? So you tune parameter, etc. You need to make it justify. Okay. Yeah, I see 27 students still there. I hope they are not just hanging there. So, okay, yeah, so that's it for today. Thank you. See you next week. And if you have any question, just send me email. Bye.